We are starting chapter 5 on integrals. First, we want to talk about the some notation we're going to need to define what's called a Riemann sum, which defines the definite integral. So first, let's talk about sigma notation. May have seen this before in algebra, but let's review. So you basically have uppercase sigma and lowercase sigma for the Greek alphabet. And so this is what we use for the uppercase. And it basically is S and means sum. So we use it as the idea for a sum. And so if you have the sigma notation like that, hold on a second. Let's try to make this look nice. So you have the sum, and then you have an index. You can put whatever variable you want. Sometimes we use I or n or k. Is I goes from the starting point 1 and then to n of a sub I. So this is where the index would go here. Those have to match. Okay, so let's just highlight those. Those match. All right, so then that sum means you add them up. You add, so the index usually runs from on integers. Most of the time, and what we use is positive integers. It could start at 0, and technically could be negative, but it doesn't really make sense to do it like that, because you're usually counting like 1, 2, or you could start at 0 and do 0, 1, 2, 3, etc. But what this will mean is a1 plus a2, a sub 2, plus etc., all the way to a sub n. So that's what the sum means. I is called the index. And you could write kind of whatever. You could do the sum as, say, k goes from 3 to 6 of pi, the number pi, to the k. How about that? So what that would mean is pi cubed plus pi to the 4th plus pi to the 5th plus pi to the 6th. And that's pretty much all you could do with that one, because that's an irrational number. All right, so then here's another one. You could have like the sum of as I goes from 1 to n of f of x sub I, and then you could have delta x. So this could basically represent some constant value, and maybe it doesn't change. Now that basically can come out, but it will be in each term. So that would be equal to fx1 delta x plus fx2 delta x, etc., all the way to fxn delta x. It could be a subscript on that as well. Some properties, we need to know those. So the first property, so the rules are page 260 in our book. So you have a couple of them. So you have this one, you have the sum as I goes from 1 to n of k a sub I. Basically means you can just factor the k out. So it'd be similar to this one here, where we have this same delta x in here. So you could just factor that same thing out of every term. It's a common factor, basically. So you can bring that constant out in front. I goes from 1 to n, a sub I, like that. Okay, second one is a sum, plus or minus. The sum a sub I plus or minus b sub I means you can break up the sum a sub I plus the sum b sub I. And it doesn't matter really the index in that case. And in either case, plus or minus. Let's see. Another one, 3, you have a sum of just a constant. Then you're adding, let's suppose you're going from 1 to n this time. So you're adding that thing c plus c plus c n times. So it's basically c plus c all the way to c. And then there's basically n occurrences of that, n times. So that's n times c is what we would know that as. All right. A couple theorems that you would prove in college algebra using induction. The sum of the first n numbers as I goes from 1 to n. So if you add all those up, it's n times n plus 1 over 2. So you would take the last term, add 1, multiply, then divide by 2. It would be if you wanted to add up basically n integers. Okay, and you can prove that using induction. Then another one, the sum I squared. I goes from 1 to n. This one is n plus 1, 2n plus 1, all over 6. So, I'm just kind of showing you that some of these properties we would have seen in other areas. Okay, so that's the summation notation. There's more to see, but not a lot to really go over there. Let's get to what we're getting at. So this is kind of 5.3 as well. So 5.3 is sigma notation, definite integral, kind of doing these together. There's a lot. They give you a lot of pages here where we don't need to do so many pages, basically. So we're still kind of on 5.2, but so just put it back up here, I guess. We're doing these kind of together. Let's just take that away. Don't need that. All right, so this is what we want to start talking about. Essentially, the area of a plane or planar region. So if you have a coordinate system, x and y, like this, and if you have a nice geometric shape, say from, I don't know, 1, 2, 3, 4 into 4, and you go from 2 to 4. So if you have this nice region in the xy plane to add up, it's relatively easy to do so. All you have to do, so we're looking for area, right? So all you got to do here is break this up into regions like this. Let's see, that looks good. And you have this top region up here like this, and then you have the bottom. So you just break it up. You do area 1 plus area 2. We will do something like that as well for our integration, but this is how you can do it. And so you could actually calculate those pretty straightforward, pretty easily by doing both of them. And it wouldn't matter how jagged it is. You could break it up if these are nice geometric shapes like this. So you're basically doing area 1 is a triangle plus area 2. So area total area is area of 1, which is a triangle, plus area 2. Now, we want to figure out a way to find the area. Basically, is where we start. Talk about a way to find the area of a shape that is as a function. So you have a function up here. Suppose you have, that's called f, right? We call that f. And we want to find the area under the curve from A to B. But now this is a nice smooth curve up here. It's not a geometric shape. So it varies infinitely from A to B, this part right here. But we're looking for this area. Okay, so we're looking for what this area is under the curve. All right, so okay, so that's our goal. So what we do is we essentially break up this interval and figure out individual pieces. Okay, and we got to define this very carefully, but we're going to break this up and look at these rectangles in here. I'll show you another example in a second. Excuse me. So these rectangles are going to go up here like this, and we look at these little pieces. Okay, so that's how we're going to do it. Then we're going to add all those up. So I don't get into a whole lot of detail in 5.3 where they do left hand, right hand, and a bunch of rules. But I want to show you the basic concepts of them before we get into the integration. So let's look at these two cases. We're going to look at this one case, and I'm going to copy exactly the same graph. I'm going to draw this, and then I'll copy it. So draw in some sort of graph just like I have over there. It doesn't really matter what it looks like, just something like that. Okay, we'll call this f of x my function, and we'll go from, say, here to here. And normally you say a to b. We can leave that off for now. Okay, so we're going to look at this region between the x-axis and the y-axis. All right, so I'm going to copy that. So rewrite this exact thing. Right there, that looks good. Over here. So first, if I take the little rectangles and I go up like this, but I stop before I get to the top, like that. All of these rectangles, and for now I'll make them uniform distance apart. All of these rectangles, in this case, are inside the curve. Okay, so that's not supposed to slope like that, right there. Okay, so we go up to the top, we draw in these rectangles like this. That's not what I want. Okay, and then up to the next one would be here. And you keep going. Okay, I'm just going to draw these in. Try to make it too detailed because it takes forever. Okay, so all of these, we're going to add all these up, and we can all agree that will approximate the area under the curve. So we're going to call one of these rectangles the ith or kth intervals. It depends on what we're using. So we'll call this delta x sub I. And we're going to pick a value here. We're going to pick the value right there that's, we're going to call it m sub I, that goes up to the, just touches, doesn't go above it, but just touches below the graph. And then this function value up here is f of m sub I. That's the height. That's this distance from here to here, the height of the rectangle, this rectangle. All right, so then my delta x sub I is this width. Okay, so, well, actually, let me just write it like this. So this is the width, this is the height. So area of a rectangle is, so this one, this area, we'll call it just a, so area, and we'll call this under. So everything's under the curve, or we call that inscribed. So these are inscribed rectangles. And for this one, on the right side, what we're going to do is look at rectangles that go above everything. So we're going to go up to here, like this, and then up to here, and over here, like that, like that. So all of these rectangles, these are outside. So you can see they go above the graph. So you're overestimating, right, the area under the curve if you do it this way. So all these little pieces in here, all these little pieces are overestimating. In this case over here, this is an underestimation of the actual area, right? And so you have you do the same thing. You're going to have your delta x sub I as this width, and then you have a height. Now this time the height's going to go to here. That's your, usually they call that capital M sub I, is that height. So this is, we'll call this area over, and that's called a circumscribed rectangle. It's on the outside. So what we know then is the actual area is between those, right? I mean, the actual area of under the curve is between this underestimation and this overestimation. So basically, there's a theorem that says if you take a limit of both of these, and we'll talk about that, then you get the actual. So that's basically what we're going to end up doing. And we're going to get a little detailed on this because I want you to, when you move forward in Calc 2, for many of you, most of you, you want to be able to understand the Riemann sum and how the Riemann indefinite integral is defined. Okay, so here's the idea. So within, let me just keep going a little bit here. Each interval, there exists, when backwards E means there exists, a maximum and minimum. So this is how I'm basically not just talking, I'm going to define stuff. So within each of these little intervals, there exists a max and a minimum. That's the extreme value theorem. Okay. So we're going to let f of m sub I equal the minimum. That's the left-hand side. And we're going to do that in the ith interval. Okay, the ith interval would look like this. It's the interval x sub I minus 1 to x sub I. That's how we would write it. And then similarly, we're going to have f of capital M sub I equal the maximum value. That's the overestimation over here. Okay, in the ith interval. All right, so same ith interval. So the area is equal to length times width. The area of one of those rectangles is length times width. So this area here, oops, it's a little large. This area is length times width. And so we basically have the smaller area on the left, larger area on the right. And then there's a theorem. I'm not going to write all these details for the theorem, but basically, if we take a limit as n approaches infinity of the index, the upper sum and lower sum are equal. So the upper sum and lower sum are equal. All right, so what we're going to look at is this Riemann sum concept. I keep saying that. We're going to define it. We got to define a couple more things. So here's a definition, another definition we're going to use. So we're going to choose C sub I in the ith interval, x sub I minus 1 to x sub I. I'm setting up kind of what we're doing in a second here, in the future here. So we're not going to do endpoints. This is just giving you the concept of what's going on. We got the lower limit, upper limit, inscribed, circumscribed, and we're going to choose some C value in the interval. Either there could be an endpoint, anywhere in between. We're going to let it be arbitrary. Okay, so let me just emphasize, be any arbitrary value in the interval, right? That's the point. So then area is equal to the limit as n approaches infinity of the sum as I goes from 1 to n of f of C sub I delta x sub I, where delta x sub I equals b minus a over n. So that's now realize that's a definition. We're basically agreeing that would make it be the sum. So if we did that and you take a limit, you will get the actual area of this thing. So what we want to, so you're adding all those pieces up essentially. All right. So the way we do this for the next thing we do is we look at what's called a partition. So we need to start with an interval from A to B and partition that interval. So another definition. So we're defining a partition. So a partition, and they use like a delta. So partition delta of a closed interval A to B is any decomposition, like breakup, of the interval AB. Doesn't have to be uniform. The way we define this one up here is basically uniform. You're taking each of these delta x sub i's and you're breaking it up, like equally breaking it up. Kind of like that. A partition does not have to be that way. And there's reasons we do this. I'll explain that as we get there. But so we take any decomposition of AB into the form will look like this. So you take the left endpoint, x naught to x sub 1. And the next one will be x sub 1 to x sub 2, etc., like that. X sub 2 to x sub 3. Then we get to x sub n minus 1 to x sub n. And that's where n starts at 1, 2, etc. Another way to write that is a is equal to the x sub naught, which is less than x1, which is less than x2, etc., less than, etc., all the way to x sub n minus 1, which is less than x sub n, and that equals b. All right, so the length of the kth interval is the delta x sub I, or delta k. You could use I there, but that's okay. We're going to use k. So the length of the kth interval is delta x sub k. And so your kth interval is your x sub k minus 1 to x sub k. So that's your kth interval. And it would make sense that delta x sub k is equal to x sub k minus x sub k minus 1. So it's the next one minus the previous. Furthermore, next definition, continuing really, the largest delta x sub I is called the norm of the partition. So the largest of those deltas, so the largest of delta x1, delta x2, etc., to delta xn is called the norm of the partition. You're going to see that throughout the rest of the book. Okay, we're going to talk about the norm of the partition and what's going to happen to the norm. What do we want to have happen to the largest one? So think about this. We're not going to define it really like this. We're going to want the largest one to approach 0. We're going to want the norm to approach 0 is our goal, what we'll end up doing. So largest of those intervals is called the norm. And so the norm also is, you would say, norm of P, like that. And so partition, we'll say like a partition P. So this, sometimes we call this partition like that. We'll say, for obvious reasons, it's a P. So a general partition, what we're doing here, allows these to be different lengths, varied in length. All right, so, and there's a reason for that when we define the definite interval. Okay, let's, I think I'll go and stop here. Then next we'll define the Riemann sum, and then the definite integral. And then we get into some example. Then, yeah, that'll be about it. All right. Then we look at actual examples. So 5.4 And 5.6 is more applications, 5.5 I mean, which we want to get to for sure, get past the theory. But the theory is important to understand what's really going on. We're going to think of integration. When you look at the integral symbol, it's not a very good one. So when you look at the integral symbol, I want you to think of that as an S for sum. If you think of it like this, then it starts to make more sense. And then there's some good applications to it, of course. Okay.